Number 9.
Really?
Yeah.
Okay. Oh, yeah, probably.
And I do not have the problem with me.
Okay. Is that all it just, it didn't give a radius and you needed it? I mean, was that your question on that, Nick?
It was just, how do I approach it?
Okay. Who has the problems? Anyone? These problems can take a long time.
Because he smiles.
I mean, I'm smiling in like commiseration. Stresses in beams.
Like I got 12 problems before we get to quiz today.
Number 9. Well, you just have this body cantilever beam connected at the left. You have a torque of 15,000 Newton meters and a horizontal force to the left of 45,000 newtons. This is a solid circular cross section. So if the coordinate system's like this, then at the cross section, looking from the right towards the left, the cross section has y up, x to the left, z to the left, and then x towards us. And yeah, we need, right. And the point that we're interested in
So I guess my question
is this.
How do you analyze this? Do you put, how do you enter in the components for that?
Mm-hmm. Well, let me just go through it. I don't think this will take super long. And you do need a radius. What radius? You could put it in as a variable. Let's just give it, let's just say it has a radius of 5 centimeters. If you calculate the internal loads, well, first calculate the external loads. You get a force from the wall of 45,000 newtons this way, and a torque of 15,000 this way. Balance these. And then wherever you make the cut, you get the same thing. You have 45,000 newtons pointing to the right and a torque of 15,000 Newton meters to the left. And so you have to have a balancing force of 45,000 newtons here. So that's our T. And you have to have a balancing torque of 15,000 Newton meters here. And that's our fancy T. So this is in compression, and then you have that torque. And our total stress is equal to the stress due to tension plus the stress due to torque. The stress due to tension, it's really compression. Sigma xx is equal to the tension of negative 45,000 divided by the cross-sectional area, so pi times 0.05 squared. And what do you get for that? 5.73 times 10 to the 6 pascals and negative. So the stress tensor due to tension and compression is that in the X normal element, and then zeros everywhere else. This is Pascal's. And then the stress due to torque in our rotated coordinate system, so what I always write is the capital coordinate system, we're going to have the z-axis. Okay, so here's horizontal. We're going to have our capital z-axis going this way, and our capital y-axis going this way, where this angle is 30 degrees. Then our shear stress, capital X, Y, is equal to, we're doing this for a circular cross section, not a thin-walled tube. So this is equal to negative torque times rho, the distance from the center to the point that we care about, divided by the polar moment of inertia. The polar moment of inertia is pi over 2 times r to the fourth. Is that right? Does that look right? So can someone calculate that for r equal to 0.05? 1.0 times 10 to the minus 5. Our rho is 0.05 because we're right at the outer boundary. The torque is positive 15,000. So tau, capital X, capital Y is equal to negative 15,000 times 0.05 divided by 1.0 times 10 to the minus 5. And what do you get for that? 7.5 negative times 10 to the 7 pascals. And so in the capital coordinate system, our sigma due to torque, capitals, is 0, negative 7.5 times 10 to the 7, 0, negative 7.5 times 10 to the 7, 0, 0, 0, 0, 0. So now we have a coordinate system. So our stress due to tension compression is in a coordinate system like, let's see, this. And our stress due to torque is like this. They both have the same x-axis, so it turns out that you could add these, and what you're doing is just giving the stress tensor in this coordinate system, since this one only has an x normal component. If you're looking for something to waste some time think about that, you know. But the general way that we do it is take that capital coordinate system, re-express it in the lowercase coordinate system. So what kind of rotation do you need to go from here to here? Right. Yep. So to go from this to this, theta is positive 150. And we're rotating about the positive x-axis. So our rotation matrix is 1, 0, 0, 0, cosine of 150, sine of 150, then negative sine of 150, cosine of 150. Can someone do this rotation? So what you're doing is applying this transformation to this. So it's this matrix times this times the transpose of that. Okay.
0.
Okay, hold on. So in the coordinate system that we want for our final answer, so you got 0. Okay. Symmetry. Okay. 0, 0. 3.75 times 10 to the, wait, 7, right? I have 5 written. They're both 7. And then 0, 0 pascals. And so finally, our total stress is this plus this, negative 5. So negative 5.73 times 10 to the 6, positive 6.495 times 10 to the 7, 3.75 times 10 to the 7. I like to see the different significant figures everywhere. It always warms my heart. 6.495. We're standing up to the chemistry department. They can't tell us what's important and not important. Yeah. Yeah. Right. That's a good point. And if you're, yeah, that's true. And I suppose you could write, I've never written a program that, I've written a lot of programs, and I've never written one that that kept track of significant figures. And if I was having, when I was testing out my programs, if I was having trouble with round off error or whatever, my first thought was just to change everything to double floating point precision. And then if, usually that fixed it. So I don't know. In my experience, that was not something that I thought about or ever paid a price for not thinking about. Maybe someday I'll get my comeuppance, but I doubt it. Okay, so there it is. Any questions about that? Any other homework questions?
Just a kind of
Yeah.
broad question. When you're dealing with a circular cross section working on the neutral axis, what is the equation for Q? I was looking through
Oh.
the homework and you had one of the problems that came out to be like 2/3 times.
Okay, so we can come up with a formula for it. So, new question for the people watching at home, but that's usually Richard, and I made him come here by not telling him that there was no quiz. So the new question is, what's Q for a circular cross-section along the neutral axis? So you have this circular cross-section. There's the neutral axis. Here's the area above the line that we care about. This is the centroid, and then our y is this. Mm-hmm. Right. Right. So the from like a table of centroids, this would be 4r over 3 pi. Is that what you said? Okay. And then the area is pi r squared over 2. And so Q is pi r squared over 2 times 4r over 3 pi, and you get a bunch of cancellations. This 4 becomes a 2, that cancels, and you get 2r cubed over 3, and that's just always what it is. Because we can't do it for any other line for a circular cross-section. We can't calculate the stress due to shear force for any other line except the neutral axis.
Yeah,
It's in the notes. It's in my notes. It's in my stack.
Oh, yeah.
If you go to D2O, if you click on the content.
Yeah, content, course information or something.
Information
Yep.
in there, and then it has, yep.
Or if you're a stud, you can just be like, I don't have that table, and you just go like, well, what's a centroid? Not as many as I'm sure you all would think. I'm sure they did, but not out loud. And so we could do it. Are you challenging me right now? We could. Let's not.
I'll make you cry.
But yes, the formula for the centroid of a half circle or a quarter circle is 4r over 3 pi. Any other homework questions? All right. Now we're moving on to the next topic, which is macroscopic deformations and statically indeterminate structures. These go together. It's not indeterminate, it's indeterminate structures. And so what the approach that we're going to take to doing this is macroscopic deformations will go first elongation. And there are two things that this will be due to tension and compression. And then we'll also do it due to changes in temperature, which is called thermal expansion. So due to tension, compression, and thermal expansion, and the second thing is angle of twist. And this is due to torque. And then the last one is deflection. And that's due to shear force and bending moment. And I think, bending moment and shear force are related by those derivative relationships. So this shear force thing is just sort of because of their connection, that's sort of built in there, but it's really the bending moment that we use for that calculation. And so what we're talking about is if you have a beam that starts out like this, and then you apply loads to it. This is an exaggerated version, but say you apply a load there and a load there. What's the difference in the location at that point compared to the unloaded case? And, we're dealing with very small strains. Still, if you have a long beam or something, even though these angles, this angle would never get this big. But if you have a really long beam, this thing can have very tiny strains the whole way along it, still be basically horizontal at the end, and you can still get a deflection of many millimeters, So when I say macroscopic, that's what I'm talking about. You can't see the local deformation at a point, but you can visually see this deformation. Same with the angle of twist. If you have a long beam and you're applying a torque to it, that local deformation is small, but by the end, you could be talking about a few degrees of twist. That's right. Yep, exactly.
But if you were right next to it, you couldn't see it.
Well, you can't. It's like what the strain measures is the deformation, the local deformation at a single point. And so, like, if you were looking at the change in length or angle of twist or something of a single, like you took out a Sharpie, don't do this with a plane, but if you took out a Sharpie and drew like a tiny little cube, and then as this thing deformed, you were hoping you were going to be able to see the deformations of that tiny cube. You won't see that because the deformations locally are small. But if you integrate them over a 2 meter long thing, it'll integrate into something that's visible. Okay. And the process that I'm going to follow here is for each one of these things, so elongation, angle of twist, deflection, so for each macroscopic deformation, first I'll talk about, first, let's say we'll calculate the deformation. And then we'll apply it to statically indeterminate systems. So I'm going to start by talking about elongation. I'll talk about how to calculate how far the end of a beam has moved due to elongation or contraction. And then we'll talk about how to apply that to statically indeterminate systems. And before I go into all that, statically indeterminate systems to me is one of a handful of things that you've been sort of, or for a lot of people, you've been kind of waiting to know. This is one of those sort of interesting things, I think, that you felt something missing when you went over structures. You might not even have been able to voice your concerns, but they were there. So here's the thing with statically indeterminate systems. So statically indeterminate system, motivation. This is the idea behind it. If you have a beam like this, and you know the dimensions, and there's a force applied here of 1,000 newtons, you can calculate all the external loads on that beam. And the reason you can is that the reaction loads at the wall give you 3 variables. So 3 variables, and you have 3 equations from Newton's laws. Okay, so that one works. But now think about if you had this cantilever beam and you put this 1,000 Newton force here, and you put a roller there. This is something that would be a pretty natural thing to do if you had to build this structure, and when you built it, the thing ripped off the wall, and you had to fix that. It would occur to anybody to put another support at the end to keep that from happening. But now we have a system that we can't solve using statics. Because we have 3 variables here, 2 forces and a couple, and we have a force here, and there's no way to know through statics how much of the force is taken up by this and how much of that vertical force is taken up at the wall. There's no way to do it. It's not a matter of, I mean, it's just simply a matter of having 3 equations for 4 variables. It's not something that takes experience or whatever. And that doesn't really sit right because, nothing goes weird with, it's not like this causes problems if you actually build it. And it's not like this thing starts to deflect as time goes by as if there's some weird, some kind of toggling between those forces. There's a definite determinate solution for the loads. Everything happens very predictably. We just, through statics, don't have a way to calculate what those loads are. But it turns out that, so this is 3 equations for 4 variables. And you can't solve it with statics alone. But what we can do is, if we know how this material deforms when it's loaded, then we can come up with an expression for, in this case, we'd be looking at the deflection of that beam. We'd come up with an equation for the deflection at the end of this beam under the loading here and here, okay? That would give us a new equation. Well, so we'd come up with an expression for that deflection, and then we'd say, well, since that roller's there, we know that that deflection has to add up to 0. We know something about the end here, okay? And that would give us our extra equation that lets us solve a system of 4 equations for 4 variables. And that's the relationship between these macroscopic deformations and being able to, solve these statically indeterminate problems. We'll get some group of equations through statics, and the additional equations we need are going to come from restrictions on the macroscopic deformation. So, yeah, so this thing would, I'm going to give an exaggerated version of it, but this thing would come out from the wall here, curve down, and then slowly curve back up and end up at 0 deformation there. And you can actually solve. That's really weird that happens. When I get shocked from the chair, it shorts out the. Okay, so let's start out with elongation. So I'll say this is number 1, and then the first type of elongation that we're going to deal with is due to internal tension and compression. So let's think of a beam, and we're looking at a single sort of infinitesimal slice. We're looking at this disk that starts out with a thickness dx. And the internal tension of that disk is T. So we have an internal tension T that way and T this way. And we can think of this disk as represented by the location X. So the x-axis is going this way along the beam. At some chosen x value here, we have a disk that has this infinitesimal thickness dx. And we want to know at that disk, what's the infinitesimal elongation of that disk? So if, in this case, when it's in tension, that disk is going to go from a thickness of dx to a slightly larger thickness that we're going to call dx plus du. Well, the change in thickness is going to be du. So the change in the thickness of the disk that's due to that internal tension T is du is equal to the tension times dx over EA. So A is the cross-sectional area, T is the internal tension. Let's think about how this works. So this is the formula, but let me elaborate on that. You can think of that as T over A is that's the normal stress. We're dividing by E there, so this all together is equal to the strain and then we're multiplying it by the thickness of the disk to come out with the overall change in length. If you think of the strain as like a change in length per original length, we're multiplying it back by the original length to get just the change. So then the total change in length we're going to get from integrating so the total elongation U is equal to the integral from 0 to L of T over EA dx. Most often, so this is what you would do if you have any of these values changing continuously. Okay, so if the cross-sectional area is changing, it's getting thinner as you go along, or if, well, this wouldn't change, but or if that internal tension is changing as you go along the length, then you have to integrate. But most of the time, these things are only going to change a finite number of times. So usually, the expression T over EA is constant or piecewise constant. If it's constant, what would be the simplified formula for U? Yeah, T over EA and then times the length. Because you can just pull the T over EA outside the integral, then integrate dx from 0 to L, and you get this. So this is the formula for this being constant. Or if it's piecewise constant, then this is equal to, can anyone come up with what this sum formula would be? I'll write the sum formula, you do the rest. I was the one who remembered that this is what the sum formula looks like.
L would be the thing that varies.
All of these things can vary. So it's just going to be this I, Li over, I guess we can put all these in. That E isn't really ever going to change that I can think of, but everything else could. So this is the version of it if P over EA is piecewise. Okay, so let's do an example where we have a column, and at the middle, something's applying an upward force of 3,000 newtons. And at the end, something's applying a downward force of 10,000 newtons. Change in the length of the beam. And I'll give you the other stuff you need. So we'll say the cross-sectional area is 0.01 meters squared. And E is 200 times 10 to the 9 pascals, so that's steel. And for some reason I'm giving Poisson's ratio here. Maybe I was asking for strain or something. Leave that out. Okay, so to do that, the first thing you have to do is calculate the internal tension everywhere. And you can probably guess that when we do this calculation, there's going to be one value of internal tension from the floor to the 3,000, another value from the 3,000 to the 10,000, and then we'll just use that piecewise constant formula to add up the elongation for this and the elongation for this and get the total. Yes. I had everything. 2 meters. Yeah, each of these are 1 meter. Okay, so first, well, we can think of this as I'm going to think of lining this end down over here. So we have the 10,000 Newton force here. And the 3,000 Newton force this way. And if these are in equilibrium, we know that there has to be 7,000 newtons going that way. That's not even going to come up in the calculation. But now we have to do cuts. So first, for x values between 0 and 1, we have 10,000 here and t here. Those have to add up to 0, so t is equal to negative 10,000. Makes sense that to counteract this, you have to be in compression. And so the elongation on the first piece, I'll call it U1, is equal to negative 10,000 times the length of the first piece divided by E. So 200 times 10 to the 9 times A, 0.01. And you get a value of 3. Nope, that's the other one. Negative 5 times 10 to the minus 6. And what are the units here? Yeah, we're talking about distances, so this is meters, exactly. And then cut 2 is for x between 1 and 2. We still have the 10,000. Now we have the 3,000 this way. And so t is equal to negative 7,000. You don't have to see that. You could write out Newton's second law and just calculate it the way we've been doing. These are like super easy internal loads problems. And then use that to calculate the elongation in the second piece. So U2 is equal to negative 7,000 times 1 divided by 200 times 10 to the 9 times 0.01. And you get negative 3.5 times 10 to the minus 6 meters. And so the total elongation is those two added together, negative 5 times 10 to the minus 6 minus 3.5 times 10 to the minus 6. So negative 8.5 times 10 to the minus 6 meters. And so if you loaded this bar this way and then measured how much this had deformed, you would see that the top of this bar had gone down 8.5 microns. Any questions about that? Yes.
Are we skipping this completely?
I will skip it, and then we'll just do the next one that's scheduled. Any other questions? Okay. No school tomorrow, so don't come. Yeah, exactly. And I think also most of you are